Hi, everybody. I'm Kfir. I'm the chief scientist at Basis Technology. We are based mostly in Cambridge, Massachusetts, and we have a few R&D centers around the world. One of them is in Israel, in Tel Aviv, and this is where I'm based. And today I will talk about how we keep up with evolving languages. So natural language processing, NLP, is all about processing text completely unstructured, either to find some structured information, as you can see here, like, for example, named entity recognition, or to generate an alternative text, like in the case of machine translation or text summarization. The output format is defined by what we would call an NLP task. Now, the input text could be anything between a formal news article and an informal instant message or SMS. So in this session in particular, I'm going to focus on how we build models that can handle multiple domains and multiple genres. So there are many NLP tasks out there that people try to solve. So I took this list from nlpprogress.com. If you're not familiar with it, I recommend you to go and check it out. This is a partial list that I took from there, and usually those tasks are provided along with some state-of-the-art results and recent papers. Many research teams around the world are competing on state-of-the-art results for all these tasks, and they're mostly taking kind of a transfer learning approaches recently, using all these autoregressive models that you see on the screen, and they're coming very fast these days. So I had to put this this image. Sometimes we feel a little bit like Jon Snow here. But anyway, in the industry, we're interested mostly on some of those tasks, like, for example, sentiment analysis, summarization, classification, and of course, named entity recognition, which is probably one of the most important tasks in NLP for commercial users. So in this session, I will focus mostly on named entity recognition. So let me give you a clear definition of the problem first. Named entity recognition is all about finding names of people, organizations, locations, and some other types in written language, in running text, written in different languages. So let me give you an example. Elon Musk says building the first sustainable city on Mars will take 1,000 starships in 20 years. So you can see here that Elon Musk highlighted in blue, right? This is a name of a person, and Mars highlighted in pink, that's the name of a location. Now, that's the kind of output that we would like to get from when we try to solve named entity recognition. Now, maybe some of you think that this is just a simple task. Why don't you just compile a list of location names and then, something maybe from Wikipedia, something like that, and then just use a simple lookup procedure to find all instances of that list in the text, and we're done. But then obviously you won't know whether Mars is mentioned at the location or the candy bar, right? You really need some context in order to resolve this kind of ambiguities. I have more examples like that. So I'm based in Israel, and Israel has since become most associated with, let's put an ending to this sentence, let's say citrus fruits. Or maybe some other stuff, high technology, delicious hummus dishes, too many elections, and so on, right? But all these texts can actually define that Israel here is actually the state of Israel. It's the name of a location, if you like, a geopolitical entity. But what if we pick a different ending to this sentence, something like jazz pianist Bill Evans? So now Israel becomes something else. This is not the state of Israel. This is actually a name of a jazz standard written by this guy, Bill Evans, right? So it's all about context and ambiguity. So it's definitely not a simple task. Another example for you, maybe this one. Here, the ambiguity comes from the time where we use those names. So I would say that before 2017, if you said the names Bert and Elmo, you're probably referring to these guys from Sesame Street. But after 2017, especially in this community, right, probably referring to these large autoregressive models that people use today to solve many NLP problems. Basically, named entity recognition or detecting entities in a document is probably, as I said before, one of the most important tasks, and especially if we're talking about information extraction, such as relationship extraction, where we want to extract entities from or relationships between pair of entities, or event extraction, sentiment analysis, and some other similar tasks. In this sense, I would say that entities are kind of the backbone of a document or even a collection of documents. At Basis, we have a bunch of capabilities around this task. Specifically, we employ two main data-driven algorithms to detect entities. The first one is based on a recurrent neural network, and the second one is based on a more kind of traditional machine learning algorithm. That's what we use specifically is structured average perceptron. And we're using this algorithm for many years now. It's in production, many languages. And the numbers that you see here, those are the F-scores, accuracy basically calculated over evaluation data sets that we created with doing annotations. And we can definitely see that the neural model, the recurrent neural model, is better than the traditional one across all languages. But you have to keep in mind that it's also much slower, and some consumers will still prefer to use models that are faster by many factors. Now, regardless of the algorithm, all these models, in neural model as well as the perceptron-based model, they're all trained using a data set that we annotated in-house. And we annotated for all these languages, mostly news articles. From time to time, we do have some other types of documents. And those news articles, they follow a strict grammatical rules. And obviously that seems like less effective if you take those models and you try to apply them or try to use them to detect entities in instance messages, for example, because there the grammar is definitely considered as informal. So among other things, I would say that every model has the following three characteristics. So we have the language, the domain, and the genre. I will not talk about language here. It's a whole different story. But I'll focus on domain and genre in this session. A domain usually defines the content of the document, right? So like news or like general news, what we would call it, finance, medical, travel, fashion, so on. And you can think of the domain is like if you took like two documents from two different domains, they will be different typically in their content words. Content words are usually linked to nouns, verbs, adjectives, so on. And the distribution of entity types is usually different. For example, if you take financial documents, you will see probably more company names there, while if you took travel documents, there you're probably going to see more applications. The genre is is more affiliated with the style of writing. So not content words, but more functional words, right? So like prepositions, articles, and this kind of things. An article has, I would say, has a more official style of writing than a tweet, right? Which in a way is more formal than instant message, which can become very idiosyncratic at times. So let's focus now on genres for a little bit. In order to study the differences between the genres, we try to compare chunks of text of 4 different genres, what you see here. So we have news articles on the left column. We have SMS or instant messages, chat rooms, and speech transcriptions. We took a random sample of about 50,000 words of each corpus, which we use for calculating a few things that I will show you next. The news articles that we're using here were taken from some popular news media outlets. Instant messages were donated, same for chat room messages, which were sampled uniformly for different demographic groups. And lastly, the speech samples that we're using here are basically meeting minutes from a specific lab at Carnegie Mellon University, which we manually transcribed, and therefore, if you think about it, the standard or the grammar and the casing is more or less consistent. Okay, so what we've seen from looking at the data is that with any informal text like chat rooms, instant messages, so on, people like to write less. Okay, so like in a compressed form. So for example, this expression, I don't know, becomes something like IDK in chat rooms, right? In instant messages, maybe something like that even, right? So people just like to write less. In speech, it's slightly different. So people also like to write less, but or to compress the message, not to write, to say less, but it's in a different form, right? Because for example, they want to say things that are easy or easier to pronounce. So IDK is more complicated than just say I don't know. So you will see different ways of compressing the message in chat rooms, instant messages, and speech transcriptions. We took the 3,000 most frequent words in each corpus, and then we calculated how many of those words are shared by every pair of corpora here. So the numbers that you see on each link here represent the percentage of shared common words in every pair of genres, which may give us some directions for how similar they are. So as you can see, the instant message collection is more similar to the speech transcription collection and of course to the chat rooms. And that makes sense, of course. They're all informal in a way. And but on the other hand, they are all less similar to news articles. Okay, so that's one insight. This is a different view, but it's similar. So here we sum the number of mentions of the K most frequent words. Okay, so, and we divide it by the number of words in each corpus. So we get a percentage, basically. That's the y-axis. And that gives us some information about the variability of the corpus, right? Because the most frequent words, usually those are the functional words that are less affiliated with content. So we use a growing number of K here, and that's the x-axis. And as an example, if you look at the green curve, that's news articles, represents news articles. You can see that the 500 most frequent words cover about 70% of the entire corpus. That still leaves us about 30% room for all other words, as opposed to all the other genres, the more informal genres, which leave much less room for all these other words which are typically affiliated with content. And also this green curve of news articles, it grows slower than all others, suggesting that news articles are more variable. I mean, the variability in content is higher, and it's just contains more content words. Another insight is that in addition to all that, we actually manually annotated about 40,000 words of each corpus for people, location, organizations, similar to what I've showed you before. And we followed our named entity recognition annotation guidelines in English. And this figure shows you the number of entities divided by the total number of words. It's not exactly 40,000 for every corpus. This is why we normalize them, and that's per genres. And basically, it shows you the density of entities, right, in each one of those corpora. And it seems like news articles, they are more dense, with almost 6% entity per word rate. But also instant messages, they're also pretty dense than what we would think of. Okay, so actually I had more such observations to share with you, but I had to cut a few slides so that we leave enough time to talk about some other things. So going back to this slide from before, now after we've done some analysis and show you some of our insights, it becomes clearer why training a model with news articles and then use it to detect entities in instant messages, for example, is probably not going to work. So we need to do something else, right? We would like to explore ways to for adapting our models to handle text of other genres and other domains. I'll briefly discuss two potential approaches for how to do that. That's what we were doing at Basis in production. And one of those ways is completely unsupervised, and that will work better for domain adaptation. And the other way is more traditional. It's a more traditional supervised machine learning, basically for building a custom model. So I will talk about each one of them. So to talk about the unsupervised one, let me first briefly discuss one difference between a traditional machine learning algorithm and a deep learning algorithm in general for NLP. So one of the differences is basically in the way that we represent the input text. In a traditional machine learning algorithm, on the left side, basically, we represent words with features that we extract using some linguistic tools. Like, for example, we break the text into words, right? Sometimes it's not that trivial. Like if you are processing Chinese, for example, there are no spaces between words, and so on. You can use part of speech tags, lemmas, word and word clusters. Word clusters are usually those clusters that gives us some information about the semantics, the meaning of the words. We put together or we group together words that share the same meaning more or less. And it's very similar to embeddings, which we use in a neural network usually to represent the input words or characters, right? So with traditional machine learning algorithm, to give more context or more information, semantic information about the words, we use word clusters, and with the deep neural network, we use word embeddings, right? Those are vectors. I'm pretty sure you're familiar with this, but those are just simple mathematical representation that captures the semantics of or the meaning of the words. So in the unsupervised approach for doing domain adaptation, we take those word clusters and embeddings and we fine-tune them for the target domain. I'm not planning to go into too many details now, but to do that, we use a large collection of documents in the target domain, but don't need labels, so labels are not required. This is just plain text. And so for the neural model, we use contextualized embeddings like BERT, specifically with BERT here, which we fine-tune for the target domain using those unlabeled documents, basically just continue training the model for the mask language model task. And for word clusters, we use Brown clustering, we just fine-tune those clusters using using a large collection of documents from the target domain. In this figure here, you can see that the original domain basically is the news or general domain, and the target domain that we are fine-tuning for is financial domain. Now, here are some results for you. This is only for the perceptron, the traditional model, not for the neural model. But still, you can see that here we have results or F scores for when we do the fine-tuning, and you have both results before fine-tuning and after fine-tuning for the financial domain. So you can see that the model can benefit from this fine-tuning step with improved F score, significant improvement. And but keep in mind that it's probably going to work better for domain adaptation because we're focusing on the semantic part, the semantic representation for words. So a little bit about the other approach, which is the supervised approach for doing adaptation. And this approach is works even for genre adaptation. So here it's a supervised machine learning. So we take a supervised machine learning approach. Therefore, we need to annotate some documents. And here we need to annotate documents for the target genre. You can see here that we had news articles and for our base model. That's the default model. And then we are annotating some chat room text for building another model. That's a different model, what we would call a custom model. And then we end up with two models. So we can take those two models and rerun them individually in parallel on the input text. And then we have another layer that kind of takes the results that are coming from each one of those models, and then it decides or it resolves conflicts in order to generate the final output. So I'm not going to provide more details now about this, how this layer works. We can do that at some other time. For some results here, here you can see for the supervised domain, supervised machine learning domain adaptation, basically. So here you can see, 4 big columns. Each one of them represents a different genre. And for each one of them, we try to combine the base model, right, to run in parallel the base model and any of the other custom models for all the other genres. So for example, if you look at the second big column, you'll see that these are the results I got for our chat rooms. So you can clearly see that adding a model, a custom model that is trained on annotated chat messages was helpful, right? And instant messages texts were also helpful for chats. This is the green bar there. Of course, I mean, I would expect that because of the similarity between the two genres as we saw before. Unfortunately, if you look at the entire picture here, the overall results on the 3 genres, the 3 informal language genres, they're not so good, and mostly because of recall. So usually the recall is pretty low, and I guess the inconsistent structure and grammar and casing and the fact that the language can be very idiosyncratic at times, probably those are the main reasons for the low scores. And I have to say that it's also pretty difficult. Sometimes it's pretty difficult for humans to actually succeed in this task. For now, we only had one annotator who did all this work, but we plan to add another one or maybe two more annotators and then measure the level of success and agreement between them and see how difficult this task is for humans. But overall, we do see improvements when adding some relevant annotated documents in the specific genre, and that's encouraging. And so we plan to annotate more documents and see how much improvement we can make with more documents. One more observation, if you like, you can see that adding the annotated documents of the informal genres was detrimental for news articles, for the news article domain. The precision actually went down. You can see that's the first large column on the left side. And that's actually, that was expected due to the difference or the different characteristics of the informal genres. We did another experiment for domain adaptation. So the same one that I showed you before with unsupervised approach. So here again, we have news articles, which we use to train a vanilla or a default model, base model. That's what you see in blue here. And then we evaluated the model on financial news. And then on, you can see in red, this is like where we use a combination of two models, one trained on news data and one trained on the financial documents. You can clearly see that adding the financial articles and building that custom model was a good move for the financial domain. But you don't see it here. Actually, it also added a couple of points to the accuracy when evaluated on the news evaluation set. And that's probably because the two domains, they're more or less similar, right? Financial news and general news, they're kind of similar. Okay, so I think I will summarize now. I hope that I was able to show you or stress out the fact that improving state-of-the-art results for the traditional named entity recognition task is not the only thing that matters. The ability to succeed in other domains and genres is crucial in the real world, right? When you go and use the models in real time for solving real problems. And that's very important for most of the players in the industry. Therefore, it's important that we continue exploring domain and genre adaptation for named entity recognitions and for other NLP tasks, and that's what we are planning to do at Basis. So thank you so much for listening, and I'll be around for taking questions, and thank you so much. Bye-bye.